Welcome back to Integral Calculus. In this video, I wanted to talk about substitution. Substitution is integration's answer to the chain rule from differentiation. Let me get my head out of the way and remind you. In a derivative, if we are trying to take the derivative of f of some function u of x, we get f prime of u of x times u prime of x. And so, if I want to integrate both sides of this equation, well, the integral of the derivative, by the fundamental theorem of calculus, is going to cancel out, and we're going to get f of u of x plus some constant of integration that's going to show up somewhere, so why not here? And then we'll have the integral of f prime of u of x times u prime of x times dx. Then from here, we're going to just simplify terminology a little bit, because u of x is just an awful lot to write out. So what if we just called it u? And then likewise, u prime of x times dx is a lot to write out. So what if we just called it du? All right, well, that might seem a little bit strange at first, but it again makes sense. Well, the integral of du should be u plus some constant of integration. And the integral of u prime of x dx should be u of x, again, plus some constant of integration. All right, the first one here, just because integrating a differential just gets you the thing that you're dealing with. The second one, the fundamental theorem of calculus. The integral of a derivative is the original function. That's what we used over here. So the notation is just giving us two different ways of writing the same thing and just compressing it a little bit. So if we are given an integral in a form that is messy, and we happen to have gotten lucky in how our form is messy, we can use this method of substitution in order to perform our integration. So for example, if I have x times the square root of 9 minus x squared dx, I notice right away, and the thing I want you to notice right away when you are looking at this, is there's kind of two functions going on, right? There's the x, and then there's a square root of a nasty mess. The more complicated of these is square root of nasty mess. So I want to kind of just isolate square root of 9 minus x squared. And that is itself a composition. F of u is the square root of u. U of x is 9 minus x squared. Once we got to this point, now we're ready to start filling in the things we need to do the substitution. So I need to know what u is. I also need to know what du is. Well, du is u prime of x dx. That's the definition of du. What is u? Well, we know what u is, so u prime we can just differentiate. It's going to be negative 2x dx. Now we look at the integral at hand. We have u, that's pretty nice. For du, we have some of it, but not all of it, right? We have a dx, we have an x, we don't have a negative 2. But negative 2 isn't too hard to come by. I can multiply by negative 2 and divide by negative 2 at the same time. Multiplying and dividing cancel each other out. Now I've got a negative 2 inside the integral, and since 2 is a constant, the negative 1/2 can come outside of the integral, and nothing has changed, but I've made this work in a way that is going to be in my favor. So I've got a negative 1/2, and I've got the integral of the square root of u du. The integral of square root of u, right? Use the power rule here. Square root of u is u to the 1/2 power. So then the power rule from there, we're going to end up with 2/3 times u to the 3/2 power plus some arbitrary constant of integration. Distribute the negative 1/2 across, so it'll be negative 1/3 u to the 3/2 power. And then here's one of the places that people tend to really get mixed up trying to deal with integration. C is an arbitrary constant. C can be any value you would like it to be. Well, if I multiply that value by 1/2, it's going to be a different value. But if you know I'm going to multiply it by 1/2, you can pick the value of c so that negative 1/2 times c is the thing you want it to be. We're just going to cut out the middleman. We're still going to call it c. The c here and the c here are different arbitrary constants, but they're still arbitrary constants, and we don't need to worry about that difference. We don't have to name it. We don't have to think about it. We just accept it's there. All right. One thing left to do here. U is not what was given to us in the original expression. X is what was given to us in the original expression. So we have to take that value, plug it back in over here. And there is the solution to this indefinite integral. All right, how about one more? We did an indefinite integral. We should probably also look at a definite integral. Definite integrals are interesting in their own right for several reasons. One of my favorite of which is that it gives me an excuse to play around with some limits of integration. So how about the integral from 0 to 1 of two dx over 2x plus 5, the whole thing squared. Again, the thing that I notice here right away is that there's a lot of mess going on. And the fact that I have stuff in composition down here is really speaking to me. So maybe letting u be 2x plus 5 would be very useful to me. And then if I do that, du, the derivative of 2x plus 5 is just 2 times dx. But here, because this is a definite integral, I have limits of integration to deal with. The limits of integration are given to me as values for x. Some people really like just going through and doing the u-substitution and getting back to x the same way you do in the indefinite integral. I have seen too many people forget to do that last step. And by too many people, I mean myself. And so what I do instead is, let's evaluate my new function here, u, at those limits of integration, 1 and 0. when u is 1, I'm sorry, when x is 1, u is 7. When x is 0, u is 5. With that information, when I do my u-substitution, my limits of integration change. When x is 0, u is 5. When x is 1, u is 7. 2 dx is du. 2x plus 5 is u. And from here, I can use the power rule, no issues. You might find it useful to rewrite that using signed exponents. All right, negative 2 plus 1 is negative 1, so we're going to have 1 over negative 1, which is just a negative. U to the negative first, and evaluate that at our limits of integration. So it's going to be negative 7 to the negative 1 is 1/7, and 5 to the negative 1 is 1/5. Let's see. 1/5 minus 1/7, so that's going to be 7 over 35 minus 5 over 35, which is 2 over 35. Just finding some common denominators there. All right, so that's the basic idea of all of this. And it helps if I write the right thing down. Sorry about that. All right, so I'd like you to take a look at this one. The integral from 3 to 4 of x dx over the square root of 25 minus x squared. Seeing as it's in this video, it should be obvious that substitution is the right choice, but I want you to think for a minute and make sure you understand why substitution is a good choice here. Then go ahead and use the method of substitution, see what you end up with, and I'll see you in the next video.